When you connect to a server using SSH keys, you never actually send your password or anything secret at all. The server authenticates you using only your public key, which you could post on a billboard and still be completely secure. SSH keys are a pair of mathematically linked files, a public key and a private key, that work together to prove your identity without you ever transmitting a secret over the network. Think of it like a padlock and a key. You give someone your open padlock, that's your public key. They lock something with it. Only your physical key can open it. You can hand out copies of that padlock to anyone. The actual key never leaves your possession. That's exactly how this works. The public key encrypts a challenge. Only the private key can respond correctly. Passwords get stolen. They get brute forced, phished, leaked in database dumps, reused across services. Every time a password travels over a network connection, even an encrypted one, it's a credential that could theoretically be intercepted or replayed. SSH key authentication sidesteps that entire attack surface. The private key never moves. Nothing sensitive is transmitted. The server never sees your secret. This matters everywhere, connecting to Linux servers on AWS or DigitalOcean, pushing code to GitHub, running automated deployment pipelines, configuring remote machines in a DevOps workflow. And when teams skip key-based authentication and rely on shared passwords for server access, it eventually bites them. One breach, and every system that password touched is compromised simultaneously. Here's the actual sequence when you run ssuser@yourserver.com with key-based authentication configured. First, your SSH client sends your public key to the server, or more accurately, presents it as a claim. I have the corresponding private key. The server checks its authorized keys file, which is literally a plain text file sitting at bets SSH authorized keys on the server. If your public key is listed there, the server knows you're a recognized identity. But it doesn't just take your word for it. The server generates a random piece of data, called a challenge, and encrypts it using your public key. Only someone holding the matching private key can decrypt it. The server sends that encrypted challenge to your client. Your SSH client decrypts the challenge using your private key, which never left your machine. It then sends back a cryptographic response, technically a hash of the decrypted value combined with the session identifier, proving it could read the challenge without revealing the private key itself. The server verifies the response. If it checks out, you're in. No password exchanged, no secret transmitted. Your key pair is typically generated with SSH keygin, TED2555519, ED25519 being a modern elliptic curve algorithm that's both fast and cryptographically strong. This produces two files, IDED25519. Your private key, guard this carefully, and IDED2551.pub. Your public key, safe to share freely. If this is the kind of deep dive you want on infrastructure and security concepts, Stack Future publishes one of these every day. You copy the public key to a server using SSH copy ID user at yourserver.com, which appends it to that authorized keys file automatically. From that point on, your client authenticates by proving it holds the private key without ever handing it over. You spin up a new Ubuntu droplet on DigitalOcean, you try connecting and get permission denied, public key, which is actually a good sign. It means password authentication is already disabled, but your key isn't registered yet. You run SSH keygin TED25519. See your email example.com locally to generate your key pair. Then you add your public key, the contents of IDED2551.pub, to the server's SSH authorized keys file, either through DigitalOcean's control panel during setup or manually via a console session. Now, when you run SSH root at your server IP, the handshake happens automatically. If your private key is protected with a passphrase, which it should be, your local SSH agent handles decryption, so you only type that passphrase once per session, not on every connection. Same process applies to GitHub. You add your public key in GitHub's SSH key settings. Then Git push over SSH authenticates you with the key pair instead of a password or personal access token. SSH key authentication works because you never send anything secret. You prove ownership of a private key by solving a challenge that only you could solve. The public key is a lock. The private key is the only thing that opens it. Remember those two files, what each one does, and you understand the whole system. If you want to go deeper, asymmetric encryption, the math underlying all of this, is worth understanding on its own. If this clicked, hit the like button. It genuinely helps.